Okay, so we are done with defining what convergence in a sequence of real numbers is. So now I'm just going to talk a little bit about subsequence. Okay, a subsequence of a sequence. Right. So sharing, share. Okay. So if you look at definition 3.4.2, yeah. So it gives you a kind of formal way of saying what a subsequence is. Generally, this is very simple. If you have a sequence, so for the example given there, now sometimes for this kind of sequence, I will just write it as follows, right? So I don't write this indexing anymore, yeah, just for to be brief, okay. So later you will see that I will primarily write it in this form, okay. Now this sequence, right? You will give you 1/2, 1/4, 1/6, 1/8, and so on, right? So this is basically a sequence of reciprocal of even numbers, right? If you want to take a subsequence, you can create a subsequence from this sequence by deletion, okay? So if you delete those that cannot be expressed in this form, okay, so I think it has to be 1/2k, yeah. In the notes, I forgot the 1/, okay? So just take note of that. So so if it cannot be expressed as 1/2 power k, you will delete, right? So we check the first one. Is it okay, right? So k equals to 1, you can express. This one k equals to 2. Now this one cannot, right? Because it's 2 times 3, right? So you delete this. This one you can, right? So it's k equals to 3 and so on, right? So one more is like 1/10. So 2 times 5, so you can't express it as 1/2 power k, so you delete, right? So after you delete all this, the subsequence is a subsequence. Sorry, a subsequence of this. Okay, right? So this subsequence is actually nested inside a larger sequence. Okay, it's just this is something similar to a subset. All right, so we talk about sets. You have subsets, right? You talk about sequence, they also have subsequences. All right, it's a similar concept. Now, here, once you have the subsequence properly defined, why do we have such things? It's because suppose sometimes you want to show that some subsequence, some sequence, right, converges. Okay, but you find that it's actually quite difficult to show this because of the particular form of xn. Okay, it may be complicated to show. So one strategy is to see that if your xn is a subsequence of, let's say, maybe I just put x prime n. Okay, if you can express that xn is a subsequence of some other larger sequence, and the larger sequence converges, okay, And if the larger sequence converges, then you show that xn converges. All right. So this is some useful idea. Yeah. If you want to show that a particular subsequence converges, but it's too hard to show, you may be able to find a nesting, right, of the subsequence in some larger sequence. And then sometimes the larger sequence is easier to show that it converges, right? So then you just show that the larger sequence converges, and therefore your subsequence also converge. Okay, that's the idea. All right, so very clearly, if you want to show that this, of course, it's very easy to see that this sequence converges to 0, right? So in this case, it's actually trivial, right? But clearly, this you can also argue that 1 over 2 power of k converges because it's a subsequence of 1 over 2n, and 1 over 2n converges to 0. Okay, you can also argue like that. All right, so is it clear to everyone, subsequences and their properties?
Yes, doctor.
Okay, this is actually quite simple, yeah. Okay, so the next thing is boundedness, right? So this is just a basically definition of boundedness of sequences. So the sequences can be bounded above.
Before that, doctor.
Yeah.
I have a question on page 18 of the note.
Page 18. Yeah. Okay. What question is that?
The first item and then the second equation, the operation, is it actually equal?
Which one? Is it item number 2?
Or subsets of that.
Statement number 2.
Item number 1, but equation number 2. Yeah, statement number 2.
No, it's not equality. It's not an equality.
Oh.
It's not.
So it's a subset.
Yeah. It's a subset.
Oh, okay.
Yeah.
Then why is item number 2 and item number 4 is different? Because item number 2 has an intersection operation, while number 4 doesn't have that.
They are actually well, they are different functions, right? One is the inverse image, right? So they're different.
Yep.
Yeah, the two is a function, but 4 is it is actually the inverse. It is an inverse mapping. So they're not the same thing.
Oh, okay. All right. Okay, thank you, doctor.
Okay. Okay. So okay, boundedness. So you can say that your sequence, right, is bounded above if and only if there is some number, right, such that all the elements in your sequence, right, they cannot exceed. They are at most equal to this number m, right? So for example, this sequence, the sequence of natural numbers, is not bounded, right? So it's not bounded. Because you cannot find, it will just keep on going to infinity, right? So there's nothing to kind of like stop it from progressing, okay? But of course, this sequence will be bounded, okay? This sequence is bounded, right? Because as your n becomes larger and larger, right? So this sequence is what? 1 over 3, 2 over 5, 3 over 7, and so on, right? So you'll be bounded. You see that it's actually increasing, right? But it cannot go out of what value? Anybody wants to try? So this is bounded by what? Anybody wants to try? As your n becomes larger, right, what will happen to this term? Yeah? Anybody?
Um, n over 2n is larger than n over 2n plus 1, so we can know that the thing is strictly less than 1 over.
Sorry? So this sequence, right, will be, okay, this sequence of numbers will be bounded by some value here, right? Towards the end, you see that it cannot go out of certain value. So what should this value be?
1 over 2.
Sorry?
1 over 2.
1 over 2, okay. Others? Is there only one solution? So you look at this carefully, right? So it just says that it is bounded, right? So it just doesn't go further than some number, okay? So this bound it doesn't have to be the sharp bound. 1 over 2 is what we call a sharp bound, right? In fact, your soup of this, okay, soup will be equal to 1 over 2. Okay, is the soup, all right? It's not a max because you don't have a max here because this is not exactly equal to some number, right? Okay, but you have the soup, right? Because the soup is the supremum is the smallest upper bound, right? Okay, other possibilities are 1, any value actually, there are actually many values, okay? 1, 2, and also everything okay. They are all upper bounds of xn. Okay, so you look at the definition carefully. It just says that it's bounded above if and only if there is an m in R, such that all the elements, right, xn, right, they cannot they are actually restricted by this m. Okay. So as long as you can find some m, right, it's okay already. Although we often will prefer to work with the sharp bound, right, the soup. But as long as when you say it's bounded, as long as you know that it cannot go out of some value, doesn't matter what that value is. There could be many other candidates. Then it's bounded, right? Bounded above. Then you also have bounded below, right? Bounded below is basically just from the below lah, right? So like for example, you have 1 over 2, 1 over 4, 1 over 6, right? The sequence of reciprocal even numbers. So this is 1 over n, right? So it's bounded from below by what? 0, right? Okay, it's definitely larger than 0, right? So I would say that so it is actually bounded from below. The equality sign is not necessary to be present, all right? As long as the equality is just to cover the case where it might actually be equal to the bound itself, but it doesn't have to be, all right? So in fact, in this case, the infimum of 1 over n is equal to 0, okay? Okay, so then you have xn is bounded if and only if it's bounded above than below. So you say bounded means is above and below. Okay. So for example, this sequence, right? Is it bounded? Is this sequence bounded?
Yes.
Yes, right? Because it's bounded below by 0, right? Okay, its infimum is 0. What is its supremum?
1.
1, right? The largest is 1, right? So it cannot go more than 1 and it cannot go below 0. So it's kind of like trapped between 0 and 1. So you just think of a bound as like some kind of a prison, yeah? Some kind of prison for the numbers to keep the numbers, prevent the numbers from going wild all over the place. Okay, so bounds are useful because they keep the numbers in check. Yeah, otherwise if your number go all over the way, then it's hard to know yeah, properties, right? Especially if you want to make certain calculations. Okay, so these are the bounds. Yeah, like for example, this one, the bound, this is also bounded, right? Because it's infimum. What is the infimum of this sequence? Anyone?
One over three.
Yeah, correct. 1/3, right? Smallest, right? This sequence is actually, if you plot this sequence, if you make this sequence, is kind of like going up like this. And towards the end that are larger, it kind of like stabilizes. It converges to 1/2. Okay, so definitely it is bounded. The sequence is bounded above by 1/2 and bounded below by 1/3. Okay, it's just a prison, yeah, to restrict the range of the numbers, the sequence. Okay. Okay, then I give you a theorem. Every convergence sequence is bounded. Okay, so this is actually quite intuitive, this statement. If the sequence is convergent, then it's surely to be bounded. All right. I have the argument that's the proof there. You can actually read the proof. So you just try to read the proof on your own, yeah. I think it's quite clear. So again, the proof you are using a device called triangle inequality. Okay, that inequality is very useful, yeah. So you managed to show that. I just want to illustrate the proof, right? In theorem 3.4.2 is an illustration of the proof using a specific example. Okay. So let me just sketch that. Okay, so I have this particular example. It's my n. So my numbers are going from this is my xn. Okay, going from 1 until this one is 3.1 something, the square root of 10. So my numbers are going like this. Okay. Okay, so I'm until 10, yeah. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So up to this point, 10, yeah. This is 1. Okay. So the sequence, it doesn't matter. Your sequence can go, it can have something like this, and then after that, it only starts something like this. Okay. So clearly over here for this sequence, right? So if you look at the tail behavior first, tail behavior, all right, there is some n greater than the threshold n. So here in this case, your threshold is 10. For this part, right, when this is true, right, for the tail, yeah, for the tail, right, if I use an epsilon of 0.5, so here this convergence is to 1.5, okay. So epsilon of 0.5 means your threshold is here, okay. 1.5 plus 0.5, it goes to 2, yeah, and it goes to 1 here, okay. So it's for the tail here, for the tail part here, you know that they deviate, right? They are deviation from the value that they converge to, right? They cannot get out of plus minus 2. Sorry, they can't get out of, they can't get away from it by more than 0.5 epsilon. Okay, that's clear, huh? All right. So you know that the tail sequence is bounded above by 2 and bounded below by 1. All right. And how about the sequence in front of it? Okay, before the tail. So that will be from 1 to 10. Okay, so this sequence may have a different kind of property. It doesn't matter because convergent sequences, right? It is actually a tail behavior. All right, it doesn't. We don't care what happens in the front. Okay, because you're going. It's a property of the sequence when n tends to infinity. So it's a tail behavior. So in this case, how about the behavior in the front? Doesn't matter. We don't care. Like it can increase to some number here, right? And it will be bounded anyhow. Okay, so here it will be bounded by what will this be? This will be bounded by square root of 10. Yeah. Okay. So for the sequence from 1 to 10, they are bounded by square root of 10. Okay. For the tail sequence, they are bounded by above by 2. So the whole sequence, right, is bounded by either you take whichever one is larger. So max of square root of 10 and 2 is square root of 10. Yeah. So the whole sequence, right, you see that is bounded by square root of 10, right? Because it just cannot go out of square root of 10. At most, it reaches square root of 10 when n is equal to 10. And after that, it never exceeds that. Okay? So this gives you a specific example and the idea of the max. All right? The max of the elements of x, okay, before your threshold value. Okay? The point is the whole sequence is bounded by either the upper bound for the sequence in front or the upper bound of the tail sequence. It actually another example will be something like this. You could have some sequence like this, and after that some sequence like that. Okay, so for the tail, right? So this is the tail. So it converges to some value a here, right? Okay. So for here, okay. So this is your threshold. Sorry, the threshold n is here. Okay. Now so this is your m, right? Okay, the largest among the values here. So that's m. So here you have your, so this is the a, right? So above here will be a plus epsilon, and below here will be a minus epsilon, right? So anyhow, your whole sequence, right? It cannot exceed it cannot exceed a plus epsilon. Okay. So the bound will be, you choose the larger one, right? M or a plus epsilon. So in this case, clearly it is a plus epsilon. Okay. Right. It's definitely bounded. So if you make your epsilon arbitrarily small, so the bound will be just a. Yeah. Okay. All right. Then we move on to the example of some sequence of numbers where there is actually no limit. So it's not there's no convergence. Yeah. So the example given there is so this, of course, this one we know that it has no limit because you basically just have minus 1, 1, minus 1, 1. Okay, there's no limit. So how to prove this? Okay, so the proof is by contradiction. All right, so you do by contradiction. So you will suppose that has a limit, right? If it has a limit, then you will have minus 1 minus a, right? Okay, so less than epsilon, all right, for some n greater than equals to the threshold. Since you only want to derive a contradiction, you just need to show one particular example, yeah? So you keep the thing simple by using epsilon equals to 1. Okay, then you consider two cases. The odd n, when your n is odd, you will have minus 1 minus a less than 1, right? So you get 1 plus a less than 1. Okay. If you have even n, so this will be 1 minus a less than 1. All right. But you have 2, right? Is equal to, we know there's 1 plus 1. And I can write it as 1 plus a plus 1 minus a, right? So this one, after that, we apply the triangle inequality. So we'll get this. Okay. And since this is less than 1, this is less than 1. So this will be less than 1 plus 1 equals to 2. So you basically are saying that 2 is less than 2, which is absurd, right? Okay. So that means your assumption here is actually wrong, yeah? Because by making this assumption, you got something that's absurd. So definitely this assumption is wrong. The assumption that it has a limit is wrong. So the contrary is true, right? The contrary is that it doesn't have a limit. Okay, this is the way to argue using contradiction, which is useful if there are only 2 possible outcomes. All right, you have to be very sure there are only 2 possible outcomes. If you have more than 2 outcomes, then not so effective. Okay, because you still don't know which one there are. Like, for example, if there are 3 outcomes, right? You assume that one of the outcome is true. Okay, you derive a contradiction. At most, you just know that one of the outcome is not true, but you don't know which one is correct, right? There are remaining 2. Okay, but it's very effective if there are only 2 outcomes. All right. And then you have a definition there, 3.4.4, monotone convergence theorem. Okay, which basically says the following: if your sequence xn is increasing and bounded above, or decreasing and bounded below, then it has a finite limit. Okay, this is very intuitive, this result. If your sequence is increasing and bounded above, it has a finite limit, sure. And if it is decreasing and bounded below, it also has a finite limit, sure. Okay, so then there's an example there, 3.4.6. So if your A is larger than Z, is for some positive number, right? A power of 1 over n converges to 1 as n tends to infinity. So how do we prove this? Okay, so the simplest one is to break the proof into 3 parts, yeah, because your A, right, there are 3 cases. One is when your A is between 0 and 1 fraction. So this is a case number 3 in the notes. Okay, talk about the simple cases first. A equals to 1 and then A larger than 1, right? Okay, so when A equals to 1, so you are covering all cases, yeah? Okay, A greater than 0, there are 3 cases here, right? And these 3 cases cover the case of A greater than 0, right? Because A greater than 0 is, this set is the same as this set union, this set union, this set, okay? So we'll talk about these 3 cases separately so that the idea is clear. So case 1 is this one, yeah? When your A is equal to 1, then this is trivial, right? Because so then your A power 1 over n is 1 power 1 over n, right? And this is equal to 1, right? Because your the base number here is 1, yeah? Anything raised to the power, so no matter what your n is, so this is basically a fraction, right? A root. So 1 over 2 square root and 1 over 3 cube root and so on of 1 is still 1, okay? So you prove that. Okay, so it doesn't change, right? So this sequence of number will just be 1, 1, 1, 1, okay? So you prove the case. The second case is A greater than 1. Now, when your A is greater than 1, like for example, something like 2, right? Okay, or 3, or whatever, right? What happens is that you note that your A power 1 over n is decreasing. And how do you know it's decreasing? Because if you look at the log, right? Its log form is this, right? So this is decreasing, isn't it? Okay, decreases as n increases. Okay, so since your so this log form and the A, they are actually monotone, yeah? The log function is monotone. So if your log function is decreasing, therefore it implies that this A is also decreasing. Okay. All right, and it's bounded below, yeah. So okay, in order to use the monotone convergence theorem, it requires the sequence to be decreasing and bounded below. So clearly, this thing here is definitely larger than 0, yeah. So it's bounded from below, very easily shown. So therefore, by the monotone convergence theorem, this exists, okay? There's a finite limit exists. All right. Now, if it exists, right, then we need to find it, okay? So let's try to find it. Okay, so to show that the limit exists, so we want to show the following, right? That the limit is 1, yeah? Okay, so we need to show this. So for all epsilon, this is true for some n greater than a threshold, okay? Now, to show that this is not so easy to work with, yeah? To show that this is true, we show the equivalent, which is we show the log form. If this converges to -1, right? So log A over n, which is its log form, will converge to 0, yeah? Right? If your A power of 1 over n converges to 1, you take the log form, it should converge to 0, yeah? Okay? All right, so this is easy to show because then therefore this is basically just, okay? So no difficulties, yeah? This log A is just a constant. So it's bounded from above by the same thing, but with the threshold here. So you just need to choose n larger than log A over epsilon. Okay, so then you have the limit. You show that the limit exists and it converges to 1. The case number 3 is when you're dealing with a fraction, right? So let's see. Okay, so this case, yeah. So when you're dealing with a fraction, so 1 over a will be larger than 1, right? So why do we do this? Because 1 over a is larger than 1, it will then, you can then borrow the result from this case. So therefore, limit of a, okay, is equal to 1, so the limit of 1 over this, okay? So I just write it like this, yeah? So then this, since the numerator is a constant, so this is equal to the following. Okay, but since your 1 over a is greater than 1, right? So basically this one is following this case already, right? Doesn't matter, you can think of it as a b with b greater than 1, right? So you use the result of case 2, right? So it will be 1 over 1, so which is 1. Okay. So the idea of showing this proof is that to give you some idea how to think about showing things very clearly, okay? How to make the argument watertight. All right. So in this case, it will be easier to partition your argument into 3 parts because then they'll be easier to do. Okay. So this is one of the possible ways to use when you try to make proofs. Yeah. Okay. So so I think we covered the section on 3.4. Okay. Do you have any questions for me? We're going to take a 10-minute break now before we move to the topic of limits, supremum, and infimum, which is something new for you. Okay, but not very hard. Okay. But before that, let's hear from you if you have anything you want to ask about the section on 3.4. Okay, sequences. Any question from any of you? Parvin? Any question from you, Parvin?
So far, okay, doctor.
Shaswani? Any question from you? Shaswani? Here? Ivy? Any problem from you, Ivy? Question?
Doctor, can you explain the last part?
The last part, which part is it?
Um, the B.
B.
Yeah.
You mean this part here?
Yes.
This thing? Which B are you talking about? Is it this one?
Yeah, that one.
Well, this 1 over A, right? Because your A is since your A is between 0 and 1, right? So you take the reciprocal, it will be some value larger than 1. Okay. So you can think of this 1 over A as some kind of, you can express it as B, right? And this will be the case of B larger than 1. So basically it will be equivalent to this case. This is well, I'm just saying that it is I'm just replacing 1 over A with B, and then saying that is B greater than 1 is equivalent to this case, right? If you are able to handle like 1 over A, 1 over A is some case larger than 1, so it already falls into this case, then it's fine already. It's just to make from here we want to make use of the result 2, yeah, because it doesn't matter, right? This A is basically just some number, right? So it's just saying that 1 over A, so this whole thing, this whole number is greater than 1. And it's the same as saying case 2, right? You're dealing with a number that is greater than 1. Okay, like here, right? This is a number greater than 1. So I'm also dealing with a number that's greater than 1 here. All right?
Okay, thank you, Doctor.
Okay. All right, so, okay, so let's take a break now. Come back, do some stretching, and then come back after 10 minutes, okay? Okay, so in this hour, so we're going to talk about something new called limits supremum and infimum. Okay. Okay. So if you follow, so I'm going to just walk you through definition 3.5.1, right? So suppose you have xn, a sequence of real numbers, right? So we will say that a sequence of real numbers. Okay. So we will say the following, yeah. Lim sup, limit supremum, right? So we will usually just say lim sup. Okay. This is when we write something like this, limit supremum, right? Lim sup of xn, we mean the following. Okay. we have another one, limit infimum, lim inf is defined as the following. Okay. I use a term called extended real number, yeah. Extended real number basically means that it's any number that is between an extended real number x, right? So your x can be any real number, and it can also include it will treat the infinity as a number. Okay, that's why it's called an extended real number. It adds infinity as a member. All right, although infinity is used as a concept in mathematics, but in this case, it might be convenient to treat it as a member of the, what we call that, an extended real number, yeah? Which means your lim sup and lim inf can actually be infinity, okay, plus minus infinity. Okay, so let's try to see, so this is the definition. So let's try to see them in action, right? So to see them in action, we look at example 3.5.1, right? So if you have this sequence, right? Okay, so we want to find the lim sup, all right? To find the lim sup, we first have to find this quantity, right? The supremum of the sequence, yeah? X, so note that this is xk, okay? This is k. So basically this part here, right, means is actually the tail, yeah? It's the tail sequence, right? The tail sequence starting from some index n. So if you have some sequence like x1, x2, you have xn, maybe maybe this xn minus 1, xn plus 1, xn plus 2, and so on, right? You have this sequence. So this supremum x index k greater than or equals to n means that you are considering this tail sequence here, yeah. You are basically you don't care about this part, okay. In fact, limiting processes always talk about the tail behavior, okay. So it's saying that starting from some k, right? Starting from k equals to n, right? That means starting from this tail, what is its limit, right? You don't want to talk about those at the beginning, okay? Right? You take the so over here, right? So you take this sequence, and then you'll find its supremum. Okay, the supremum of this tail sequence. After you find the supremum, you let it take limit. Okay, so in this case here, so the supremum of minus 1 power k. So this one is basically just 1, right? Okay, for all n in the set of natural numbers, because this sequence, right, is basically minus 1, 1, minus 1, 1, and so on, right? Okay, so towards the, so it will just keep on repeating this pattern, right? Okay, so suppose you have any tail here. Let's say this is your tail, right? All right. So this is your tail. Now the supremum of this tail, right, is definitely 1, right? Okay, because it just moves around minus 1 and 1. Okay, the supremum is definitely 1. So when you do supremum and things like that, please don't try to do it as an algebraic method, like you move things around. Okay, it generally it may actually not work, because this part here requires you to understand the idea of the supremum, and then that you're dealing with the supremum of the tail sequence. Okay, so it may be better to write down the sequence and then highlight the tail region, and then from there find the supremum. Okay, usually that once you do that, it will be much easier. So once you know that the supremum is this, right? Therefore, the lim sup of the limit supremum, okay, as n tends to infinity will be equal to 1, right? Because this is a constant, so when you take limit, it's still the same, right? Limiting process taken on the constant will not change the constant, okay? And then you have the infimum of the tail sequence. So definitely this will be -1, right? Very clear. Therefore, your lim inf of the tail sequence, sorry, this will be, this is n. Okay. So this will be equal to -1. Okay. So in this case, your lim sup and your lim inf are different, yeah. And in fact, when the when your sequence is actually not convergent, your lim sup and your lim inf will be different. Okay, so later we have a result showing that if your sequence is convergent, then your lim sup is equal to a lim inf. And if the lim sup is equal to lim inf, it can be used to show convergence as well. So it's an if and only if kind of relationship. Okay. And then yeah, that's shown in theorem 3.5.1. Yeah. So let me clear this. So your theorem 3.5.1, right? So you have xn is a sequence of real numbers. Okay, real numbers, and your x is an extended real number, right? So yeah, meaning it can take positive, negative, infinity as a number. Okay, so xn in the limit tends to x as n tends to infinity if and only if, yeah, lim sup xn is equal to the lim inf xn is equal to x. Okay, so that means if you show this condition, you can imply that you can imply convergence. Okay. On the other hand, if you show that convergence, then you can imply the lim sup and the lim inf are the same values. Okay, that means you don't actually need to go and find the sup of the tail and then take limit, right? Because from here you already have the result. Okay. So the if and only if is very convenient, yeah, because it allows you to make use of this result in both directions. Okay. So so you can look at example 3.5.2. Okay, so I have a sequence here, n over n squared plus 1, right? So so here, so if you apply, okay, so what I did there was that I found the lim sup and the lim inf, right? Okay, so I'm using this part and I try to infer convergence. Okay. So I know that the tail sequence, right? So this sequence will be 1, 2. Sorry, it will be. Let's erase that. 1 over 2, 2 over 5, 3 over 10, and so on. Then you have. Here I have n squared plus 1, n plus 1, n plus 1 square plus 1, and so on, right? So basically, I'm only interested in the tail sequence here. So I have we call that I find a supremum, right? Okay, supremum of this. Okay. So basically, it's talking about this tail sequence here, right? So what should this be? So you know that the this sequence is decreasing, right? Because the denominator is quadratic, right? The numerator is linear. So the denominator is going to increase much faster than the numerator, right? So therefore, this whole tail sequence is going to rapidly tend to 0, okay? Therefore, the supremum among this tail sequence here, right, must be the first term here, which is n over n squared plus 1, okay? All right. Therefore, your lim sup of this, sorry, n squared plus 1 here is the limit of the supremum here, right? By definition, so you have this, okay? So this will give you 0, okay? You can get this to be 0 very easily, right? All of you know how to do this, right? Is it clear to everyone how it is done? Oh, anyone wants to explain why it's equal to 0?
We can differentiate the numerator and the denominator, so it will become 1 over 2n. So basically, this thing will become 0.
Okay. Who was talking just now?
Yeah, it's me.
Oh, 1. Is it 1?
Yeah, yes, it's me.
Okay. Yeah, so that the method that I used just now is L'Hopital's rule, right? You basically apply L'Hopital's rule. Because if you substitute n here, so here is a case of infinity over infinity. So what you did just now was L'Hopital's rule, okay? All right. It's one way to do it, but you have to be careful with L'Hopital's rule condition. There are only some forms that you can, if you make the substitution, you can actually get certain case like this. This is what we call indeterminate form, yeah? So then you can you can take the derivative, right? So in this case, it is limit. You differentiate n is 1, you differentiate it is 2n, right? So 0, okay? If you don't know L'Hopital's rule, how would you argue that this is equal to 0? I mean, I won't ask you like why, because you can just, when you explain things, you can just simply write, if there's a limit here, you can just write, is it at 0, I'll accept it, right? It's just that I want you to make sure that you know what is going on, right? So either you can apply L'Hopital's rule, or more at a more elementary level, how would you justify that this is definitely 0? Like without going through all that. Of course, you can also do this limit by using the, you can prove it more rigorously, but it's not necessary here. Okay. So what's the other approach?
Doctor, just now, as you said, the numerator is linear and the denominator is quadratic. So the denominator is like moving faster than numerator, so it will go to 0.
Yeah. So this is more like a qualitative explanation, right? Which I think is comparing the speed of movement, right? So the denominator is increasing much faster than the numerator. So it makes sense that it should rapidly tend to 0. Okay. The other argument is that this guy here, right, is approximately n over n squared when n large, right? when n is very large, right? Because when your n is very large, you add 1 to it, no effect. Okay, so if you approximate this, so you can cancel one of the term. So n over n squared over n over n squared plus 1 is approximately 1 over n when your n is very large. And therefore, it's easy to see that as your n keeps getting larger, this will tend to 0. Okay, so there are several ways to understand this. Yeah, L'Hopital's rule may be easier in some situations where it's a bit tricky to use other kinds of arguments. It gives you a mechanism, like an operational way to deal with it, which is sometimes useful. Okay, but you have to be careful with the condition. Yeah, L'Hopital's rule can only be operated when you have this kind of indeterminate cases. Okay. All right. Okay. So then we have so limit supremum is 0. Then if we talk about the infimum of k squared plus 1. Okay, so you're talking about the infimum of this tail sequence here, right? So this is clearly 0, right? Because it will rapidly, it will actually rapidly tend to 0, right? So it's infimum, right? It's a lower bound, that is the largest will be 0. Okay, the largest lower bound, yeah. Okay, so it's a constant. Therefore, you have lim inf of n squared plus 1 is the same as lim inf of 0. So you have 0. Okay, right? So your lim sup and your lim inf are both equal to 0. And this implies that this sequence converges to 0, yeah? Okay. All right, so this gives you an operational way of dealing with the lim sup and the lim inf. There is actually another way to do it, which is based on theorem 3.5.2. All right, over there we have the following results. So the lim sup of xn can be written as instead of the limit, right? So okay, I'll just write limit sup xk, which is equal to the infimum of n supremum of xk. So this part is by definition. From here to here, there is actually a proof, but I omit it. Okay, we just use the result, right? It's enough already. Otherwise, there are too many proofs. Okay, if you're interested, you can check some books on real analysis if really interested. Otherwise, we'll just use the result here. So this is infimum, sorry. So the limit infimum of xn is infimum. So which is equivalent to supremum of the infimum. Yeah. Okay. Now sometimes this form, right, is more useful. This form here, linking the lim sup and the lim inf, is more useful than this form. Okay. So later when we study some theory, right, we may actually we need to evaluate this lim sup and lim inf, and it may be actually easier to use this result than this result. Okay, that's why we learn the identity here. All right, so look at an example that's given there. So you have a sequence n over 2n plus 3. Okay. So if you take the infimum of k greater than or equals to this, so this will k over 2k plus 3. So the sequence here will be something like 1 over 5, 2 over 7, 3 over 9, and so on. 2n plus 3. Sorry, there's no 2 there. N plus 1 over 2n plus 5 and n plus 2, 2n plus 7 and so on. Okay, so we're only concerned with the tail here. Now, so the infimum, right? So what will happen? So definitely the infimum. So this sequence is actually what's happening to this sequence? Is it increasing or decreasing? Anyone? Is it increasing? Decreasing? So what will happen if your n is getting larger and larger? So this will tend to what sort of value?
It increases.
Yeah. So it's increasing, right? Because towards the end it will converge to 1 over 2. Yeah. So the infimum of these will be the first value here, right? This is an increasing sequence, so the smallest of them will be the first value. Okay. So you will have the infimum will be n over 2n plus 3. Okay. And when you talk about the supremum of k plus 2k plus 3, so the supremum will be this part, right, towards the tail, right? So it will be 1 over 2. All right. And therefore your so lim sup xn. Now if I use the infimum part, right? So infimum of n of my supremum, right? So my supremum is 1 over 2. So definitely this is 1 over 2, right? Because it's an infimum applied on a constant, right? So nothing special there. The lim inf of xn is the supremum of the infimum, right? Which is this one. N over 2n plus 3. So again, this one is 1 over 2, right? Because this one is you substitute 1 inside, and then you substitute 2 and 3 and so on, right? So this sequence is actually increasing, right? So the supremum will be 1 over 2, yeah? Okay? So therefore your limit supremum, your lim sup and lim inf are equal to 1 over 2. Okay, they are the same, right? So we conclude that this sequence converges to 1 over 2. Okay, so this is another way to apply the to calculate your lim sup. Okay, use this approach, use this result. Okay. So any queries on a lim sup and a lim inf concept? Okay. So you try to do a few more tutorials, it should be okay. Right, tutorial questions, tutorial questions, you will be able to have more exercise. Okay. Okay, so I think we just have maybe around 10 minutes more. So so I'm just going to talk. I'm just going to talk. Introduce the idea of a sequence of functions. And if we have time, we talk about the one of its mode of convergence. Now, so far we have only been concerned with this is a sequence of numbers. Okay. Now we want to introduce a sequence of functions, which we will basically just write like this. Okay. The difference here is that this is actually a function, and it has a dependence on an argument here. All right, which I denote as x. So one example is the following. Okay, so it's totally different from the sequence of numbers. Yeah, because sequence of numbers only depends on the index n. Okay, like for example, n over n plus 1. Okay, so it only depends on n. Yeah, but this sequence of function here, it depends on both things, n and also the argument x. Okay, I gave you the example here over there, which is 1 over x. This is equal to, so this sequence, right, is equal to, so you don't touch the x here. So the x here is some value in the set of real numbers such that this function is defined. Okay, so in this case, it will be in the set of real numbers. So this function is defined. When your n is equal to 1, right? So it will be 1 over x. Okay. When your n is equal to 1, it will be 1 over x. When your n is equal to 2, so this n equals to 1, it will be 1 minus x over 2 power of 2 and 3 and so on. Okay, so it is actually a sequence of mathematical functions. Okay, if you refer to figure 3.6.1, right? So this is basic. So you can see the graph there, right? Figure 3.6.1, whereby I have a few graphs there, right? So this is actually linear, right? This is a linear function, intersect at 1. Okay, so it just this goes down like this. Okay, so for simplicity, I just graph for positive values. Okay, so this is a case of n equals to 1. Okay, now this is quadratic, right? N equals to 2. This is a quadratic function. Okay, so you have something like this. Okay, it actually touches. So when this is equal to 0, so your x is equal to what is it? 2, right? Your x, this is your f and x. Okay, this is 1. Yeah. So it touches the line here, and then after that it increases quadratically. Okay. So the case of n equals to 2. N equals to 3 will be you have something that is like flat like this, then it comes down, right? And so on and so forth, right? And then I show you one case when your n is sufficiently large, 1 over. So you find that that curve, right, is something like this. Okay, so the red one, n equals to 10. Right. So the question now is, we can ask ourselves, right? If we keep on, so this sequence of function is like you got many different functions, right? And they are progressing as your n increases. The question is towards the end, right? At the tail, right? What is this function? What will it become, right? As that means basically asking this function when n tends to infinity is equal to what? Okay, so this gives us to example 3.6.1, where I give you a result there. Okay, the result is that we know that this actually is equal to e of minus x. Is that this is actually a well-known result in elementary calculus. You have to remember this result. Okay, so we won't go through the proof and all that. That's something that is left to the calculus course. Okay, so here we are just going to repeatedly use this result. Yeah. In fact, if you have a plus here, so it will become a plus. Okay, so it will be just exponential function. So basically, so this part here is just the plus sign doesn't matter. The important part is to note that there's a 1 here. There's a argument x here that is scaled by n, and then there's a power of n here. Okay. And this gives us definition 3.6.1. All right. So when we do something like this, we call this a pointwise convergence. Pointwise convergence of a sequence of function. Right. Which I say that let E be a non-empty subset of R. So a sequence of functions. A sequence of functions is basically, right, a function fn. It maps elements in E to the set of real values. It's said to converge pointwise on E. Yeah. Okay. So we write fn converges to f pointwise on E as n tends to infinity. Usually we actually there's actually an x here, but usually it will be suppressed. Okay. Sometimes you'll find that people will just write fn and f. They basically the x there is actually suppressed. Okay. Because the idea is that you want to show the convergence of the function, and it converges regardless of what your x is. So in some books they will suppress the notation x, but it's not wrong to write it out. Okay. Okay. So you said to converge pointwise if and only if the limit exists. Okay. So this must exist. Yeah. For each x in, okay, you must show that it exists. Yeah. Okay, so by taking limit. So this one you can argue using a formal definition of the epsilon argument, or you can basically just I think by now you should be able to just apply the limit and show that, right? So pointwise convergence is actually quite easy to do. Okay. So one more example before we take a break for today will be example. Let's clear this. Example 3.6.2, where the function is x power of n. Okay, so this is my f n x. Okay, right, and my x is bounded for the case of this. So now, so my f n x, right? There are two cases here. If my x is between is actually not is a value between is a value from 0 to some value less than 1, yeah. So note this carefully, yeah. So this is not including 1, yeah. So for this interval, if I take limit, this will be equal to because this means that it's either 0 or a fraction, right? So if it's a fraction, you raise it to power of n, and n is very large, this will definitely go to 0, right? For sure, right? And if your x is equal to 1, then this is a so this is 1 power of n. So 1 power of n, doesn't matter what your n is, it will still be 1. Okay? So I would, for here, we can, what we can say is that we can say fnx converges to 0 for x in 0 to 1. Okay, so you can familiarize yourself. I can either write like this or like this. They are the same thing. Okay, this is more like a inequality notation. This is like a set notation. They are equivalent. Okay, we can say that f and x converges to 0 for this particular range of x values, and converges to 1 for x equals to 1. Okay, so it in this case, where it converges to, so in this case, where what value fn x converges to depends on x. Okay, it depends on x, yeah. If for x between these values, it converges to 0. The other, it converges to 1. Okay, so now, so that means in the limit, right? So this means that the limit of this is not continuous, right? Because when your x is 0 to 1, it is equal to 0. So I can have like x here, 0 to 1. So this is my f, okay? F being the limit of fn. Okay. For x that is from 0 to less than 1, it converges to 0. Right? It's 0 all the thing. But then when your x is equal to 1, it actually jumps up to here 1. So this function, right? This function f, right, is which is the limit, is discontinuous over the interval 0, 1. Okay, because at 1, right, it actually jumps up, right? So there's actually this discontinuity there. Okay, so pointwise convergence cannot preserve the property of continuity, right? So the continuity of your limit, right? Limit of Fn is not guaranteed when you have pointwise convergence. Okay, so these are the two properties that are illustrated by example 3.6.2. Okay, so because there are some of these properties that are undesirable. Okay, so for pointwise convergence of sequence of functions, it has some drawbacks, right? If we use this concept, because then you cannot preserve continuity, and also there's a dependence on the value of x. So this motivated the development of the concept of uniform convergence. So we will talk about this on Friday. Now this is the convergence concept for sequence of functions that is very useful. By defining this concept of uniform convergence, if your sequence of functions has this property, then it has a lot of interesting mathematical properties. Okay, which we will look at on this Friday. Okay, you can actually do a bit of reading first. Yeah, definition 3.6.2 and onwards, page 28. Okay, onwards. It's not very hard, but maybe something new to you. All right. Okay. So I think so. It's just right, nice on time, 12:50. Yeah. Any questions that you want to ask me before we sign off?
Can you please just repeat your last two sentences because it cut off? My internet was bad. You said that we're gonna try something in what?
You mean uniform convergence?
Oh, was it the uniform convergence?
Yeah, I was just saying.
It's something that it's new, but it's not difficult.
Yeah, uniform convergence.
All right, thank you.
Yeah, because you're talking about a different kind of concept of convergence, which is just so far when we learn the convergence in sequence of real numbers, right? So that convergence concept is actually the same as pointwise convergence. Okay, nothing new. So, but then applying that convergence definition to sequence of functions produces mathematical properties that are not very desirable. Okay, so that motivated the mathematicians to develop a better idea of convergence called the uniform convergence. So once this property is found to be present, then there are a lot of things you can do, right? Some of the things that you can do will be something like this. You may have come across it. You take a limit of some integral. Okay, you have a limit operation, you have an integration operation. If you have uniform convergence, yeah, if your sequence is uniformly convergent, you can do something like this. You swap the order of, yeah, you can swap limit and integration, and it will work. But only if your Fn is having this property. Okay, so yeah, so a lot of times when you see these kind of operations, right, if the student has not studied anything about sequences of functions, when they see limit integration, they might actually kind of like automatically do something like this, right? But then they have no justification for it. They don't know why. It just seems that something that can be done. Yes, the nice thing is that it actually can be done, and it will actually give you the correct answer. But only if your function here is uniformly convergent. So that allows us to do a lot of new work, yeah, with this kind of concept. Okay, this one we'll talk about it on Friday. All right. Okay. So I think yeah. So we'll just stop here for today. All right. Okay. So thank you for listening, and I will stop the recording now.
Thank you so much, Doctor.
Okay, you're welcome. Please remember to sign your attendance in Spectrum. Yeah.